I'll talk about North Atlantic variability in the Met Office ocean reanalysis GLOW-C. And do I, here? No, here. And does this actually work? Printer does work. Which one? Ah, that one. Okay. So what is GLOW-C? Well, GLOW-C is the seasonal forecast system of the Met Office. I'll talk about a particular variation of it. GLOW-C, Global Coupled 2 version of it, but that's kind of that's a minor detail when you get down to it. The GLOW-C 5 seasonal forecast system is essentially has an M216 atmosphere and land surface module, along with a quarter of the Orca 025 ocean and sea ice model coupled together in a fully coupled and initialized forecast. The forecast will be, and is, I guess, already a contributor to the C3S seasonal forecast system of Copernicus. It currently, as Chris explained on Tuesday, is the provider of the CMEMS coupled ocean forecast, 7-day forecast. The global ocean analysis I'll be mostly talking about here will also be a contributor to the CMEMS global reanalysis. And at the same time, that ocean reanalysis has provided the boundary conditions for the Northwest Shelf reanalysis, although it doesn't provide the boundary conditions for the Northwest Shelf real-time analysis, since that's done from our North Atlantic model, which in turn is taken from our foam analysis. As with all seasonal forecast systems, we do what is known as a Hindcast or a reforecast, which supports the Hindcast. It's used to calibrate the forecast and correct model bias and estimate skill. We do this for the period 1993 to 2015. In order to make our system easily updatable, these hindcasts are usually run operationally, although the actual ocean analysis has always been done ahead of time. So that is our seasonal forecast system. A little bit, as I said, these are initialized forecasts, 6 months forecasts. The forecasts are initialized from comparable products, so our forecast is initialized from the Met Office NWP 4D VAR atmospheric analysis, whereas the hindcast is initialized with the ERA interim atmospheric analysis. And now the ocean, we have the foam, our forecast ocean assimilation model to initialize the forecast, and our hindcast is initialized by what I'll call the GLOW-C 5 ocean and sea ice analysis. Throughout this talk, and whenever you talk to Met Office people, you may hear the GLOW-C 5 ocean analysis and the foam ocean analysis being used interchangeably. And then other times they're used as separate entities, and well, they're both right. The GLOW-C 5 ocean analysis and foam analysis are the same. They use exactly the same model. They use exactly the same assimilation system. The only way they really differ is that they use different surface forcing conditions. And so, for instance, the GLOW-C 5 ocean analysis uses, well, they both use core bulk forcing, that the atmospheric parameters that go into that are provided by the ERA interim atmosphere for the GLOW-C 5 ocean analysis, and for the foam ocean analysis, they come from the Met Office and the WP analysis again. There's also some issues about that one is not the continuation of the other, but again, that's a minor detail. So what that may affect is, of course, things that are not assimilated, so it could affect sea ice thickness. They could differ slightly between the two products. It could affect surface salinity. So again, they could differ between the two products. The obvious solution to that is to actually assimilate those products or assimilate observations of those fields, and that is work that we are working towards, although we are still probably several years away from assimilating sea ice thickness and surface salinity. So that's the introduction to the models. Oh, except for one thing, last thing. And so this is a slide showing the various observations that have gone into the analysis. It's a wee bit of a cheat because this is actually the observations that I've taken this slide from one of Matt Martin's, so it's actually the slides that have gone into real-time analysis. And so, for instance, the temperature and salinity profiles are more attuned to more recent Argo type measure, the prolificity of Argo measurements, as opposed to what you might have seen in terms of those profiles at the beginning of the analysis in 1995. But the satellite data has been fairly constant throughout, so that's not as big of a lie as the profiles are, perhaps. And so we have, as you can see, we have 3D temperature profiles and salinity profiles, mainly coming from the EN4 analysis. Yes, that's correct, for even the Geo5 product I'm talking about here. We use the ICOAD surface data, primarily in the reanalysis. We use the Pathfinder, NOAA, AVHR, along with the ATSR products while they exist. Although at certain periods we also use the MEDOP and AMS and AMSRI products as well. And we also assimilate sea ice concentration coming from OCSAF and altimeter data coming from the variety of altimeters that have consist in the Aviso V3 product for this case. So that's the setup for the system. The first thing I'm going to talk about in terms of the performance of the analysis in the North Atlantic is actually an atmospheric quantity, and it's also the forecast of that atmospheric quantity. So in some senses, you can ask me, what's that got to do with the reanalysis? Well, I hope at the end you'll agree with me that it does have something to do with that. So the first thing is this North Atlantic oscillation. What is the North Atlantic oscillation? The North Atlantic oscillation is essentially the seesaw between temperatures in Europe and Greenland. That is essentially, don't bother to read the part in the green, but it's essentially, the point was that it's been known for it was known by the Vikings 1,000 years ago that you had this seesaw between warm temperatures in Europe and cold temperatures in Greenland and vice versa. And essentially what it is a measure of is the strength of the westerlies across the North Atlantic. So your default setup is of course the Azorian high and the Iceland low, which gives you westerlies across the North Atlantic. When those are stronger than normal, then of course you have stronger winds across the North Atlantic, and traditionally a very zonal jet stream at the same time. When the jet stream gets disturbed and you have, oops, that actually does work, doesn't it? Not when you want it to. When that's disturbed, when you have a disturbed meandering jet stream, you can have blocking in the North Atlantic, so you can actually have highs in the North Atlantic, blocking highs in the North Atlantic, disturbing your westerly flow across the Atlantic, and you can have, and that of course brings cold temperatures into Northern Europe. The meandering jet stream will bring snow down from the Arctic into the eastern seaboard of the US, and so you have a very different weather regime. And last thing I wanted to point out too, then I'll come back at the end of the talk, is of course when you have this strong positive NAO, of course you have continental winds coming into the Labrador Sea in the eastern Arctic of Canada, and so you get cold conditions in Labrador Sea, and that quite often leads to convective action in the Labrador Sea, or increased convective activity in the Labrador Sea. And that'll come back into the talks later as well. So why do we care about the NAO? Well, this is your typical high NAO type conditions where you have storms coming in off the Atlantic into Europe, and so you get flooding in the UK and flooding in Europe quite often, in the rest of Europe quite often. This is your typical negative type NAO conditions where essentially again you have this meandering jet stream, and so you have Arctic blasts into northern or into the eastern seaboard, and so this is Washington DC under a typical NAO event. And this is two more such events. This is actually last winter's. I put a star over the NAO because it was actually a fairly low NAO index as it was measured by this particular measure of doing it. But it was still essentially a westerly flow and therefore lots of wind. If you note the difference in the precipitation between the two, you can see there is a very different precipitation pattern over England. It's much more northerly, and so there's always differences, but still very much westerly flow. And again, this particular NAO followed and this negative NAO that I have here followed exactly 1 year after the previous NAO, which I'll hopefully get to again. And again brought proper winter type temperatures to Britain. And so kids can actually have fun. So why is the North Atlantic important for the NAO? Well, these right here I have the biases in a coupled model run. So this is a freely coupled model run. It's nothing, not an ocean analysis. In our Orca 1 model and in our quarter degree model. And you can see that in the 1 degree model, there's a large cold bias in the North Atlantic, basically due to the fact that the Gulf Stream is too far south. And that bias is much reduced in the quarter degree model. And when you look at the frequency of the blocking in the atmosphere in those two models, you see that the frequency of the blocking in the higher resolution model is much closer to the observations, which are the blue here, than they are in the quarter degree model in the 1 degree model under the same conditions. I should mention the final line in that graph because it's actually kind of important. If you somehow manage to get rid of this bias in here by essentially kind of pushing in those temperatures here, so you still have a 1 degree model, but you have no bias in the North Atlantic, you get this red line where you actually also do fairly well with the blocking. So it's not really the resolution of the ocean model, it's the biases in the ocean model that are important. Although the resolution probably does play a role at some point in time as well. So the mean state of the model is important. That doesn't really tell you whether or not the variability is important, but again, I'll get to that in a second. Just to show that we do get this in the analysis as well, this is now the bias in our coupled hindcast relative to the actual analysis. And so in this case, the coupled hindcast has been initialized with observations, with the analysis, and this is the difference over that first 3 months. So this is the difference in December, January, and February when we've initialized the model in November. And you can see that there are similar biases to what we saw in the previous biases in the forecast, in the hindcast are very close to the biases you see in the freely running coupled model. One thing I should point out though is you do still see a cold bias on the warm side of the Gulf Stream and a warm bias on the cold side of the Gulf Stream. So the implication is, of course, that your Gulf Stream is too wide in this quarter degree model, but that basically goes back to what Eric was saying on Tuesday, that as you get to higher and higher resolutions, of course, you can tighten up the front of the Gulf Stream. And that may actually have implications, not necessarily for the prediction of the NAO, but the ability to predict the right amplitude of the NAO. So our signal to noise problems, if you want. but we get the mean state right. So the only other question is, how about interannual variability? Well, I'm only going to focus in on one particular point here, and that is this return of negative NAO conditions that happened in December of 2010, following a very strong negative NAO in in essentially December through March of 2009-10. And that is this concept of re-emergence. So the negative NAO in winter of 2009, 2010 basically produced large cold anomalies. At this point, this is essentially in the warm. This is the regression of the NAO against sea surface temperature. So a negative NAO, of course, would give you the opposite of this. And so this is basically in the cold region of that regression pattern. And so this is under negative NAO conditions. This is the eastern seaboard of the US. You would expect colder than normal temperatures here. That possibly get, that during the summer, that cold anomaly gets submerged below the mixed layer. And the point being that it can then, come the next winter, it can re-emerge and possibly force the NAO in the process. I haven't actually proved that it is forcing the NAO. It may not, but it is in the analysis and ready to do that if it is the case. So we do have the re-emergence properly shown in the analysis. And so put that all together, and I'm at 17 minutes, so that's not too bad. You can see that we fairly effectively reproduce the NAO during our Hindcast period, the black line being the observed NAO, and the orange line being the Hindcast NAO, and more even better, if you look at the real-time forecasts of the NAO in the last couple of years, they've all been fairly positive NAOs, and we've reproduced that in our real-time forecast as well, and have effectively been able to give half-decent advice to the weather agencies, or to the people who depend upon our forecasts. So I'm gonna try and skip over this part a little bit quick, so it's not as important as the last part, but so to get the forecast of the circulation over the North Atlantic right, apparently we need to get the North Atlantic itself right. That's not rocket science, I don't think. However, to get the forecast over the North Atlantic right, we might also have to get the tropical Pacific right. And why do I say that? Well, last year was, as you presumably know, was a very strong El Nino. We actually forecast that El Nino fairly accurately, although I shouldn't take any credit for that. I mean, the analysis, you're dealing with persistence at this point, so the analysis obviously picks up the El Nino, and we can fairly well persist that into the winter months. So we do have a fairly good representation of the El Nino in our model. That's good. Is that important? And then this slide is essentially a demonstration that it may be important in terms of the forecast. And so this is two examples of essentially using a cluster analysis where you do have westerly flow across the Atlantic, and that was associated with SST leading, this is the SST leading this pattern, and it shows an El Nino type signature. That's only one of several possibilities, so there were other clusters that don't show this El Nino signature. There were other clusters that weren't westerly and showed a projection onto the El Nino, but you can always get a projection onto the El Nino. But this one was significant in that it really is, the El Nino area is really the only area in the Indian Ocean where you do have any projection onto the SST. So it's somewhat suggestive that the El Nino could be producing that. The other study was a study by Toulouse and Skyfe that found for large El Nino event, not moderate, but large El Nino events, that they essentially produce this tropical wave train in the Atlantic, and that again sets up a westerly flow across the Atlantic, or more, I guess, more northwesterly flow across the Atlantic. And so there is some implication that you could have this effect of El Nino giving you westerly flow or a positive NAOS type signature early in the winter. It doesn't actually apply late in the winter, but just early in the winter. And so our early winter prognosis, again, showed this westerly flow. We gave an increased, issued warnings of increased likelihood of heavy rain fall during December, and lo and behold, that is effectively what came to be. So that's been the one success of the GLOSI model. Now I'm actually going to talk specifically about the GLOSI 5 ocean analysis in the context of the Atlantic overturning circulation, which is, of course, this flow of north water northward, mainly through the Gulf Stream, which is cooled and densified in the North Atlantic, and then sinks and flows back southward at depth. And is, of course, part of the global ocean circulation as well. I won't say theoretical, but for the large part of our oceanography history, I suppose, the overturning has kind of been a concept that's not really been fully measured. I mean, there has been point-by-point measurements that have backed up the theory, and so there's been evidence that this overturning exists, but of course, there's been no time series of the overturning. And in particular, since global warming has been connected to changes in the overturning circulation, it's important to know if those changes are existing. And so the whole concept of this rapid array, where we can actually now measure the overturning circulation, has been quite an advancement on our knowledge of the system. And in the rapid array, essentially, they measure three different things. They measure the flow northward through the Florida Straits. That's been measured since the early 80s by cable measurements. They measure the Ekman transports due to the wind in a very shallow way. And then they also measure the southward flow due to the geostrophic, or southward geostrophic flow in the abyssal ocean. And essentially what you have here is, of course, you have a pressure gradient at depth. Depth goes from North America to the eastern boundary. It says Africa there, but it's mostly in the North Atlantic, so well, I guess it's also in the southern hemisphere as well. But you got a pressure gradient from west to east, which, of course, by geostrophy implies southward flow. And so that can be measured by having arrays on either side of on the eastern and western boundary to measure essentially the pressure, and you can calculate this southward flow, which is this purple line here, and you add them all together, which I hope is the red line, yep, which is the total overturning. So we can now measure the overturning. Of course, these are all things that the ocean analysis will also basically produce. I've excluded in this diagram the Ekman transport because the oceans, essentially our ocean analysis, are forced by winds, which will produce that Ekman transport, but the rapid analysis also uses those essentially same winds to calculate their Ekman transport, and so the Ekman transport in the analysis and in the rapid overturning is effectively the same, and so you're just adding the same to both of them if you want. So if we look at the other components, if we look at the Florida Strait transport in the rapid observations, it's a little bit higher than our particular analysis. Conversely, the upper mid-ocean in our analysis is slightly less negative than the rapid analysis. And that all has to do with, of course, the fact that, I mean, this Florida Straits is essentially a small gap between, yep, I should be finished, between North America and Bermuda, and in a quarter-degree ocean model, it's probably too much to expect that you actually restrict your flow in that small gap. And so if you actually look at the combination of Florida Straits and upper mid-ocean, you get about the right amplitude. And indeed, if you look at that itself, if you look at the AMOC minus Ekman, which is essentially the same thing as the upper mid-ocean plus Florida Straits, you can see that the overturning in the analysis is very close, especially on longer time scales, to the rapid observations. And indeed, does okay on short time scales as well. And I don't know what the correlation is, but it is fairly significantly correlated. And so we can actually reproduce the 26 north overturning in our analysis, which was basically the first demonstration of that. If we now add the Ekman component to that, as I say, you're basically adding the same thing to both, and so not surprisingly, we do even better. So we're able to reproduce this analysis, and now we're actually able to look at that in terms of what is causing it, and we can look at density anomalies in the Labrador Sea. The first one, since our density anomalies only go back to early 90s, the first one is the density anomalies in EM4. You can see that essentially when the glow-sea analysis picks up in 90s, they essentially reproduce those anomalies. So essentially we are having the same anomalies as EM4. And if you look at the relationship between the density and this black line here, which is the NAO index, over that same time period, you can see that you get a strong densification in this period where you had a strong negative NAO. Remember that strong positive NAO. Remember, strong NAO means continental winds off of Canada into the Labrador Sea, and so you get a cooling and, for that matter, a salting of the water mass in that area, and so a strong density gradient. And so we see this density gradient several in the Labrador Sea, which, if you then follow that density at depth, this is I've forgotten the depth that it was at, but it was about 1,500 meters, I believe, slightly less than 1,500 meters. You can see that those density anomalies essentially flow along the western boundary and down. And so and remember that these density anomalies, they increase the pressure on the western boundary, and so that increases the overturning. And so we have the overturning in the, and why do I keep on pressing the wrong button? And so that will increase the overturning that we saw in the early 21st century. And so we can demonstrate that these density anomalies in Labrador Sea are related to essentially the overturning that we see several years later. And so, I mean, so we could actually use that as kind of a prediction way to possibly have some prediction in much longer term. And so if you notice here, of course, this is now 2 years ago, of course, but in 2014, we had negative density anomalies, warm anomalies in this region, again, probably due to the strong negative NAO that we had in 2009 and 2010. And so you have the opposite case, and of course that is now starting to flow down, go down southward to the 26 north, and should cause a decrease in the overturning in the coming years, or possibly already. And that might be seen in some of our decadal forecasts, but I'll not go there. So yes, our GLOSY-5 ocean analysis, it can be shown that it may be somewhat responsible for our good NAO forecast. And of course, we have this first evidence of being able to predict the overturning circulation. And I'll leave it there.